I'm Kazuma Honda from Ibaraki University, Japan. Our research is electrical diagnosis technique using differential power processing converters for photovoltaic panels. Today's presentation highlights a proposed novel differential power processing converter and its diagnosis technique for photovoltaic panels, experimental verification tests using a prototype. Here is the outline of presentation. First, I will introduce partial shading issues and briefly review conventional DPP converters and diagnosis techniques. Secondly, I will describe proposed DPP converter. Finally, I will talk about experimental results using a prototype. Background. In photovoltaic panels consisting of multiple substrings connected in series, partial shading is known to trigger two serious issues. First, partial shading causes a significant reduction in power yield. In a panel, the voltage of each substring is independent, but the current must be equal. If partial shading on PV1 occurs, current of PV1 decreases due to low irradiance and PV1 can't generate current. Hence, PV1 bypassed by diode connected in parallel and no longer contributes to power generation. Second, partial shading brings on multiple maximum power points as each substring characteristic is unbalanced. Currents of MPPs are likely to be an obstacle of ordinary MPP tracking. To address partial shading issues, various kinds of differential power processing converters or voltage equalizers have been proposed and developed. The DPP converters transfer a fraction of the generated power of unshaded PV substrings to shaded ones by supplying equalization current, so all substring characteristics are virtually unified. Thus, the partial shading issues are precluded. In order to operate the system efficiently, panels should be diagnosed to detect degradation and malfunctions as early as possible. However, conventional diagnosis techniques using an IV curve tracer or thermal camera incur high cost due to maintenance personnel and expensive instruments. In recent years, an electrical diagnosis technique capable of an autonomous diagnosis based on AC impedance measurement is considered as a promising solution. An AC impedance characteristic of a substring is measured from a voltage response to a supplied AC current, and nyquist plot of a substring can be obtained by measuring AC impedance. Since the parameters of these passive elements are known to vary depending on degradation and irradiance, substrings can be diagnosed based on parameter changes. However, conventional AC impedance measurement also require expensive instruments. To achieve reduced costs, we propose electrical diagnosis technique based on AC impedance measurement using DPP converter. For AC impedance measurement using DPP converter needs to produce AC equalization currents to each substring. But conventional adjacent DPP converter, such as PWM converter, require numerous switches in proportion to the number of substrings. Meanwhile, conventional substring-to-string DPP converters, such as LLC resonant voltage multiplier, are topologically simple. However, their equalization currents cannot be controlled. To solve these issues, we propose a novel DPP converter. Proposed DPP converter. This is a proposed novel DPP converter for 3 substrings. The switch count is only 2, regardless of the number of series connected substrings. Thus, the proposed DPP converter realizes the simplified system and circuit by reducing the numbers of switches in comparison with conventional topologies. The input port is the switching leg, while there are 3 output ports of smoothing capacitors. The series resonant tank consists of the leakage inductance of the tapped inductor and resonant capacitor. The DPP converter produces 3 uniform voltages across smoothing capacitors, automatically equalizing the substring voltage. Substring voltages are dependent on the duty cycle of switches, allowing an AC current injection to substrings by sinusoidally varying the duty cycle. The DPP converter operates in equalization mode or AC impedance measurement mode. This presentation discusses the case that PV1 shaded condition. In this mode, QH is turned on. The current of the resonant tank ILKG linearly increases. The average voltage at the switching node is equal to dV storing. Meanwhile, the average voltage at the cathode pin of D1 is VPV. Hence, the sum of the average voltages of C1 and CR is dV storing minus VPV. Voltage applied to LMG is expressed as this equation. In mode 2, QL is turned on. The leakage inductor LKG and the resonance capacitor CR resonate, and ILKG sinusoidally flows through D1 and C1. Since the diode D1 conducts, the voltages of L2, L3, and the secondary winding of the tapped inductor are connected to each substring in parallel. The voltages of inductors are determined to be VPV, thus VLMG is expressed as this equation. In summary, the diode D1, which is connected in parallel with shaded substring PV1, conducts, whereas other diodes are off. Since the average current of C1 must be 0 under steady-state conditions, the average current of D1 and the secondary winding of tapped inductor are equal to the equalization current IEQ for shaded substring PV1. On the other hand, since no current through D2 and D3, the average current of L2 and L3 are 0. From the voltsec balance on LMG, voltage conversion ratio is expressed as this equation. This equation suggests that the voltage of substring can be regulated by PWM control. Besides, properly designing N can avoid extreme duty. Right-hand figure is equivalent circuit of proposed DPP converter. The equivalent circuit can be depicted as a single input multi-output converter with output voltages Vout, equivalent output resistance REQ, and blocking diodes. Replacing the Vout 1 to Vout 3 with Vout and D1 to D3 with blocking diodes, the equivalent circuit is derived. Next, let me talk about control strategy. In this mode, since the DPP converter needs to be properly controlled so that no current flow toward the unshaded substrings, the current sensorless delta V control strategy is applied to the proposed DPP converter. With the delta V controlled strategy, in order to provide equalization current to shaded substrings only, the DPP converter operates to regulate the voltage difference between shaded and unshaded substrings. Delta V should greater than the voltage drop across REQ. In this mode, the DPP converter supplies the equalization current only for the shaded substrings PV1. Meanwhile, unshaded substring voltages are higher than Vout, and therefore currents do not flow toward them. Next, for electrical diagnosis using the DPP converter, the duty cycle D is sinusoidally perturbed so that delta D is superimposed on D in order to produce AC equalization currents to each substring. AC impedance is determined from the voltage responses to the supplied AC current to the substring. In this mode, AC equalization current for all substrings. Experimental result. This is a prototype of the proposed DPP converter. The prototype was operated at 100 kHz. The experimental setup was used to measure the power conversion efficiency of the prototype. Substrings PV1 to PV3 were removed, and the variable resistor R bar was connected to Cout1 to emulate the current flow path under the PV1 shaded condition. IR bar demonstrates the equalization current IAQ. Here, you can see the measured waveforms. These waveforms were in good agreement with the theoretical ones. Here, right-hand figure is the measured output characteristics. The measured peak efficiency was as high as 92.6%. From the measured output IV characteristic, the value of REQ was calculated to be 0.450. An experimental equalization test using solar array simulators were performed emulating PV1 shaded condition. Here, left-hand figure is the individual PV substring characteristics. Individual substring characteristics used for the experiment and the mismatch in short circuit current was approximately 1.5 ampere. The panel characteristics were manually swept using an electronic load. Right-hand figure is the experimental result. The measured panel characteristics with without the DPP converter are compared. With the proposed DPP converter, the local MPP disappeared and the maximum power increased to as high as 142 watts, corresponding to 16.4% improvement. The experimental result demonstrated the enhanced energy yield by the proposed DPP converter. To facilitate the experiment in the laboratory, PV substring emulators based on the equivalent circuit were prepared. Right top figure shows configuration of the PV substring emulator. The PV substring emulator consists of series and parallel resistance, capacitor, diode, and a current source composed of an isolated DC-DC converter and a linear regulator. Right bottom is IV characteristics of the PV substring emulators used for the experiment. The currents and voltages of the substring emulators were measured using the frequency response analyzer FRA. Here are the experimental conditions. The values of passive elements were also measured using the FRA alone to compare with the proposed DPP converter. This graph shows the next plots measured by the FRA alone or by the proposed DPP converter. In this table, parameters of the passive elements were calculated from the measured next plots. The calculated parameters by the proposed DPP converter were in good agreement with those measured by the FRA alone, corresponding to errors less than 5.27%. The results demonstrated the efficacy of the proposed electrical diagnosis technique. This presentation has proposed a novel DPP converter and its diagnosis technique for photovoltaic panels. The proposed DPP converter not only precludes the partial shading issues but also offers the electrical diagnosis capability. Experimental equalization tests demonstrated increased energy yield and local MPP disappeared. Experimental AC impedance measurement tests were performed. Thank you for your attention.